A virtual private network extends a private network across a public network, such as the Internet. It enables users to send and receive data across shared or public networks as if their computing devices were directly connected to the private network, and thus are benefiting from the functionality, security and management policies of the private network. A VPN is created by establishing a virtual point-to-point connection through the use of dedicated connections, virtual tunneling protocols, or traffic encryption. A VPN spanning the Internet is similar to a wide area network. From a user perspective, the extended network resources are accessed in the same way as resources available within the private network. Traditional VPNs are characterized by a point-to-point topology, and they do not tend to support or connect broadcast domains. Therefore, communication, software, and networking, which are based on OSI Layer 2 and broadcast packets, such as NetBIOS used in Windows networking, may not be fully supported or work exactly as they would on a local area network. VPN variants, such as Virtual Private LAN Service, and Layer 2 tunneling protocols, are designed to overcome this limitation. VPNs allow employees to securely access the corporate intranet while traveling outside the office. Similarly, VPNs securely connect geographically separated offices of an organization, creating one cohesive network. VPN technology is also used by individual Internet users to secure their wireless transactions, to circumvent geo-restrictions and censorship, and to connect to proxy servers for the purpose of protecting personal identity and location. Types. Early data networks allowed VPN-style remote connectivity through dial-up modem or through leased-line connections utilizing frame relay and asynchronous transfer mode virtual circuits, provisioned through a network owned and operated by telecommunication carriers. These networks are not considered true VPNs because they passively secure the data being transmitted by the creation of logical data streams. They have been replaced by VPNs based on IP and IP, multi-protocol label switching networks, due to significant cost reductions and increased bandwidth provided by new technologies such as digital subscriber line and fiber optic networks. VPNs can be either remote access or site-to-site. In a corporate setting, remote access VPNs allow employees to access their company's intranet from home or while traveling outside the office, and site-to-site VPNs allow employees in geographically disparate offices to share one cohesive virtual network. A VPN can also be used to interconnect two similar networks over a dissimilar middle network, for example, two IPv6 networks over an IPv4 network. VPN systems may be classified by the protocols used to tunnel the traffic, the tunnel's termination point location, e.g., on the customer edge or network provider edge, whether they offer site-to-site or network-to-network connectivity, the levels of security provided, the OSI layer they present to the connecting network, such as Layer 2 circuits or Layer 3 network connectivity. Security mechanisms. VPNs cannot make online connections completely anonymous, but they can usually increase privacy and security. To prevent disclosure of private information, VPNs typically allow only authenticated remote access using tunneling protocols and encryption techniques. The VPN security model provides confidentiality such that even if the network traffic is sniffed at the packet level, an attacker would only see encrypted data. Sender authentication to prevent unauthorized users from accessing the VPN. Message integrity to detect any instances of tampering with transmitted messages. Secure VPN protocols include the following. Internet Protocol Security is initially developed by the Internet Engineering Task Force for IPv6, which was required in all standards-compliant implementations of IPv6 before RFC 6434 made it only a recommendation. This standards-based security protocol is also widely used with IPv4 and the Layer 2 tunneling protocol. Its design meets most security goals: authentication, integrity, and confidentiality. IPsec uses encryption, encapsulating an IP packet inside an IPsec packet. Encapsulation happens at the end of the tunnel, where the original IP packet is decrypted and forwarded to its intended destination. Transport layer security can tunnel an entire network's traffic or secure an individual connection. A number of vendors provide remote access VPN capabilities through SSL. An SSL VPN can connect from locations where IPsec runs into trouble with network address translation and firewall rules. Datagram transport layer security, used in Cisco AnyConnect VPN and in OpenConnect VPN to solve the issues SSL TLS has with tunneling over UDP. Microsoft's Secure Socket Tunneling Protocol tunnels point-to-point protocol or Layer 2 tunneling protocol traffic through an SSL 3.0 channel. Multipath Virtual Private Network. Regular Systems Development Company owns the registered trademark MPVPN. Secure Shell VPN. OpenShift offers VPN tunneling to secure remote connections to a network or to inter-network links. OpenServer provides a limited number of concurrent tunnels. The VPN feature itself does not support personal authentication. Authentication tunnel endpoints must be authenticated before secure VPN tunnels can be established. User-created remote access VPNs may use passwords, biometrics, two-factor authentication or other cryptographic methods. Network-to-network tunnels often use passwords or digital certificates. They permanently store the key to allow the tunnel to establish automatically, without intervention from the administrator. Routing. Tunneling protocols can operate in a point-to-point network topology that would theoretically not be considered as a VPN, because a VPN by definition is expected to support arbitrary and changing sets of network nodes. But since most router implementations support a software-defined tunnel interface, customer-provisioned VPNs often are simply defined tunnels running conventional routing protocols. Provider-provisioned VPN building blocks depending on whether a provider-provisioned VPN operates in Layer 2 or Layer 3. The building blocks described below may be L2 only, L3 only, or combine both. Multi-protocol label switching functionality blurs the L2, L3 identity. VPN and Security RFC 4026 generalize the following terms to cover L2 and L3 VPN, but they were introduced in RFC 2547. More information on the devices below can also be found in Lewis, Cisco Press. Customer devices: a device that is within a customer's network and not directly connected to the service provider's network. C devices are not aware of the VPN. Customer edge device: a device at the edge of the customer's network which provides access to the PPVPN. Sometimes it's just a demarcation point between provider and customer responsibility. Other providers allow customers to configure it. Provider edge device: AP is a device, or set of devices, at the edge of the provider network which connects to customer networks through CE devices and presents the provider's view of the customer site. Pairs are aware of the VPNs that connect through them, and maintain VPN state. Provider device: AP device operates inside the provider's core network and does not directly interface to any customer endpoint. It might, for example, provide routing for many provider-operated tunnels that belong to different customers' PPVPNs. While the P device is a key part of implementing PPVPNs, it is not itself VPN-aware and does not maintain VPN state. Its principal role is allowing the service provider to scale its PPVPN offerings, for example, by acting as an aggregation point for multiple pairs P2P connections. In such a role, often are high-capacity optical links between major locations of providers. User-visible PPVPN services. This section deals with the types of VPN considered in the IETF. OSI Layer 2 services virtual LAN, a Layer 2 technique that allow for the coexistence of multiple LAN broadcast domains, interconnected via trunks using the IEEE 802.1q trunking protocol. Other trunking protocols have been used but have become obsolete, including InterSwitch Link, IEEE 802.10, and ATM LAN emulation. Virtual Private LAN service developed by IEEE. VLANs allow multiple tagged LANs to share common trunking. VLANs frequently comprise only customer-owned facilities, whereas VPLS, as described in the above section, supports emulation of both point-to-point and point-to-multipoint topologies. The method discussed here extends Layer 2 technologies such as 802.1d and 802.1q LAN trunking to run over transport such as Metro Ethernet. As used in this context, a VPLS is a Layer 2 PPVPN, rather than a private line, emulating the full functionality of a traditional local area network. From a user standpoint, a VPLS makes it possible to interconnect several LAN segments over a packet-switched, or optical, provider core, a core transparent to the user, making the remote LAN segments behave as one single LAN. In a VPLS, the provider network emulates a learning bridge, which optionally may include VLAN service. Pseudo-wire PW is similar to VPLS, but it can provide different L2 protocols at both ends. Typically, its interface is a WAN protocol such as asynchronous transfer mode or frame relay. In contrast, when aiming to provide the appearance of a LAN contiguous between two or more locations, the virtual private LAN service or IPLS would be appropriate. Ethernet over IP tunneling. Ether-IP is an Ethernet over IP tunneling protocol specification. Ether-IP has only packet encapsulation mechanism. It has no confidentiality nor message integrity protection. Ether-IP was introduced in the FreeBSD network stack and the Soft Tether VPN server program. IP-only LAN-like service, a subset of EPLS. The CE devices must have L3 capabilities. The IPLS presents packets rather than frames. It may support IPv4 or IPv6. OSI Layer 3 PPVPN architectures. This section discusses the main architectures for PPVPNs. One where the P disambiguates duplicate addresses in a single routing instance, and the other, virtual router, in which the P contains a virtual router instance per VPN. The former approach, and its variants, have gained the most attention. One of the challenges of PPVPNs involves different customers using the same address space, especially the IPv4 private address space. The provider must be able to disambiguate overlapping addresses in the multiple customers' PPVPNs. BGP, MPLS PPVPN in the method defined by RFC 2547, BGP extensions advertise routes in the IPv4 VPN address family, which are of the form of 12-byte strings, beginning with an 8-byte route distinguisher and ending with a 4-byte IPv4 address. RGs disambiguate otherwise duplicate addresses in the same P. Pairs understand the topology of each VPN, which are interconnected with MPLS tunnels, either directly or via P routers. In MPLS terminology, the P routers are labeled switch routers without awareness of VPNs. Virtual router PPVPN. The virtual router architecture, as opposed to BGP, MPLS techniques, requires no modification to existing routing protocols such as BGP. By the provisioning of logically independent routing domains, the customer operating a VPN is completely responsible for the address space. In the various MPLS tunnels, the different PPVPNs are disambiguated by their label, but do not need routing distinguishes. Unencrypted tunnels and virtual networks may not use encryption to protect the privacy of data. While VPNs often provide security, an unencrypted overlay network does not neatly fit within the secure or trusted categorization. For example, a tunnel set up between two hosts that use generic routing encapsulation would in fact be a virtual private network, but neither secure nor trusted. Native plain text tunneling protocols include Layer 2 tunneling protocol when it is set up without IPsec point-to-point tunneling protocol or Microsoft point-to-point encryption. Trusted delivery networks. Trusted VPNs do not use cryptographic tunneling, and instead rely on the security of a single provider's network to protect the traffic. Multi-protocol label switching often overlays VPNs, often with quality of service control over a trusted delivery network. Layer 2 tunneling protocol, which is a standards-based replacement, and a compromise taking the good features from each, for two proprietary VPN protocols. Cisco's Layer 2 forwarding and Microsoft's point-to-point tunneling protocol. From the security standpoint, VPNs either trust the underlying delivery network, or must enforce security with mechanisms in the VPN itself, unless the trusted delivery network runs among physically secure sites only. Both trusted and secure models need an authentication mechanism for users to gain access to the VPN. VPNs in mobile environments. Mobile virtual private networks are used in settings where an endpoint of the VPN is not fixed to a single IP address, but instead roams across various networks such as data networks from cellular carriers or between multiple Wi-Fi access points. Mobile VPNs have been widely used in public safety, where they give law enforcement officers access to mission-critical applications, such as computer-assisted dispatch and criminal databases, while they travel between different subnets of a mobile network. They are also used in field service management and by healthcare organizations, among other industries. Increasingly, mobile VPNs are being adopted by mobile professionals who need reliable connections. They are used for roaming seamlessly across networks and in and out of wireless coverage areas without losing application sessions or dropping their secure VPN session. A conventional VPN cannot withstand such events because the network tunnel is disrupted, causing applications to disconnect, time out, or fail, or even cause the computing device itself to crash. Instead of logically tying the endpoint of the network tunnel to the physical IP address, each tunnel is bound to a permanently associated IP address at the device. The mobile VPN software handles the necessary network authentication and maintains the network sessions in a manner transparent to the application and the user. The Host Identity Protocol, under study by the Internet Engineering Task Force, is designed to support mobility of hosts by separating the role of IP addresses for host identification from their locator functionality in an IP network. With HIP, a mobile host maintains its logical connections established via the host identity identifier while associating with different IP addresses when roaming between access networks. VPN on routers. With the increasing use of VPNs, many have started deploying VPN connectivity on routers for additional security and encryption of data transmission by using various cryptographic techniques. Setting up VPN services on a router allows any connected device to use the VPN network while it is enabled. This also creates VPN services on devices that do not have native VPN clients such as smart TVs, gaming consoles, etc. Many router manufacturers, such as Cisco, Linksys, Asus, and Netgear, supply their routers with built-in VPN clients. Since these routers do not support all the major VPN protocols, such as OpenVPN, limitations Not every router compatible with open-source firmware, which depends on the built-in flash memory and processor. Firmwares like DDWRT require a minimum of flash memory and Broadcom chipsets. Setting up VPN services on a router requires a deeper knowledge of network security and careful installation. Minor misconfiguration of VPN connections can leave the network vulnerable. Performance will vary depending on the ISP and their reliability. Vulnerabilities. In November 2015, the VPN company Perfect Privacy discovered a major vulnerability, which they call port fail, affecting all VPN protocols. Port fail allows an attacker to reveal the real IP address of VPN users by using the port forwarding method. Only the VPN companies which allow port forwarding are concerned by this flaw. Networking limitations. One major limitation of traditional VPNs is that they are point-to-point, and do not tend to support or connect broadcast domains. Therefore, communication, software, and networking, which are based on Layer 2 and broadcast packets, such as NetBIOS used in Windows networking, may not be fully supported or work exactly as they would on a real LAN. Variants on VPN, such as Virtual Private LAN Service, and Layer 2 tunneling protocols, are designed to overcome this limitation.